Now, there are several situations in which you can use this particular theorem to actually compute certain probabilities that are usually harder to compute. Okay, so let's look at a particular situation where I can use conditioning to solve certain difficult to compute events. Okay, so this is a scenario. Scenario is the following. It's called the gambler's ruin problem. So let a gambler start with K dollars of capital. And a coin is tossed. So the game is the following. A coin is tossed. If a head occurs, gambler wins $1. And if tail occurs, gambler loses $1. Loses $1. And well, the game ends in one of the two situations. Game ends if gambler makes a very large sum, let's say n very much larger than k, or he gets ruined. Okay, so the question to be answered is what is the probability that the gambler is ruined? Okay. So this situation is a very famous problem, and it can be visualized in two ways, right? So one way to visualize the situation is to think of a lattice of, let's say, positive integers. K is over here somewhere, and there is n. So the gambler is starting at the lattice point K, and if a head occurs, he moves to the right. Right, so this is head occurs, and if a tail occurs, he moves one step to the left. The question to be asked is, what is the probability that he eventually lands over here, right? Now, it's not obvious that the gambler will end up over here or over here, because he could just move back and forth. And there are several paths that neither go to n or to 0. But assuming that, let's assume for the time being that one of the two possibilities occurs, either he gets ruined or he earns a large sum of money. Then the question is, what is the probability of ruin? The other way to visualize this is that the gambler is doing some sort of a walk or a random. This is a random walk, but now I will describe a different way of visualizing it. You have time on the x-axis. This is my time. And on the y-axis, you have the position of the, in the same lattice, you have the position of the walker. And he starts somewhere over here at K, and somewhere over here is n. Start. So this is position of, so suppose he starts on k and a head occurs, then he will move one step up. So he'll go to k plus 1. And then, he can move in this sort of zigzag manner. And maybe at some point, he will land up at the origin or on the x-axis, cuts the x-axis, and then he will be ruined. So this is the place where the gambler is ruined. Okay, so what does this thing have to do with conditioning? So as it is, it's not a very easy problem to solve. I know. So the idea is to compute all possible paths that land up on the origin and compare them to the total number of paths. But then the total number of paths are not quite easy to compute. In fact, there are infinitely many paths that don't go to the origin, right? For example, I could just move back and forth over here. So it's a little tricky problem. Of course, you could use some symmetry and so on, but let's do this problem with conditioning. So let A be the event that the gambler is ruined, and let B be the event. So we are going to condition to find this probability event. So we are going to condition on the event B, event that the first toss is ahead. Okay. So why are we conditioning on the first toss? So first, to solve this problem, let Pk of A, the probability that the gambler is ruined starting with K dollars of capital. And I'm going to use the law of total probability to write Pk of A is equal to Pk of A given B times probability of B plus Pk of A given B complement, which is the probability the first toss is tail. Of course, the coin is, let's say the coin is fair, then both probability of PB and PB complement is half. So this is half times plus half times, this is also half. Now, how does that help? Now, this is the probability that the gambler gets ruined starting with K dollars of capital, given that the first toss is head. But if the first toss is head, the gambler lands up at K plus 1. And now if we want to look at the probability that the gambler is ruined, given that this event has happened, is the same as computing the probability that the gambler is ruined starting with K plus $1 of capital, right? So, and if this event happens, the gambler will move to position K minus 1, and then it is the probability that the gambler gets ruined starting with K minus $1 of capital. So this is K plus 1 of A plus half Pk minus 1 of A. And this is a recurrence equation, which you might have studied in discrete math. And then there are, of course, some initial or boundary conditions. So if the gambler starts with $0 of capital, then it's already ruined. So the probability of ruin starting with $0 of capital is 1. And if he starts with a large number, capital N, then he will never get ruined because the game ends right away. So this will be 0. And so we have a recurrence equation which we can solve. I won't go into details of how to solve the recurrence equation. So this, if you solve this, you get pk of A is equal to 1 minus k over n. So this is our solution to the gambler's ruin problem. So the point is that we could solve this problem using conditioning, a problem which was, or a probability or an event which was difficult to compute, the probability of an event which was difficult to compute, we could compute it using conditioning. Okay, so that's one use of conditional probability, sort of condition on the, if you are able to condition on the right event, then you can compute certain the probabilities of certain complicated events.